Hello, we're going to start our unit on equilibrium. Keep in mind this is in the same chapter in your textbook as kinetics, but these are two very different topics. They're related, but very different topics, so they each should definitely have their own chapter in a textbook. Nevertheless, they don't in this case. All right, so let's talk about what this means, equilibrium. We're going to look at an equilibrium system from two perspectives. One being the macroscopic view. Macroscopic meaning essentially what you can see with your eyes. So what kind of observable changes are occurring to the system that is at equilibrium. And then we'll look from the submicroscopic or particulate level. So particulate level being, the molecular level, so to speak, particulate or molecular level. And in terms of if we could actually see the particles that are involved in the reaction and what they are doing. So we'll look at from both of these perspectives. Something that's important to understand, and not really understand, but to know, is that virtually all chemical and physical changes are reversible. Think about like physical change of melting, changing from a solid to a liquid. Well, the opposite of that can also occur. And so what we'll focus on in this unit are chemical changes that are reversible, not so much physical changes. So let's take a look at this example. So we have two equations here. They're obviously opposites of one another. So we have nitrogen dioxide gas reacting to produce dinitrogen tetroxide. And then we have dinitrogen tetroxide reacting to produce nitrogen dioxide gas. So here's the situation. What occurs if some NO2 is placed in a closed container, a sealed container? So you open up a container, put some NO2 in there and close it. Now, something that you should know is that NO2 is a brown gas and N2O4 is colorless. So we'll take this brown gas. It's actually one of the pollutant gases in our atmosphere, nitrogen dioxide, produced from the combustion of hydrocarbons that contain nitrogen. It's a brown gas. That's what gives us our lovely brown skies in Southern California, unfortunately. So anyways, take some of this brown gas, put it in a container, and close it up. So what happens? Well, that NO2 gas is going to react to make N2O4. Now, here's where we're going to go back to last unit and talk about kinetics and reaction rates. This reaction, we'll label it, we'll call this reaction 1 and this reaction 2. Reaction 1 is fast at first. Why? Well, of course, we talked about this. A reaction is its fastest at the beginning. Why? Well, that's when the concentrations of the reactants are at a maximum. So this reaction is fast at first, but it slows down as time goes by, again, because the concentration of NO2 decreases. It's being used up. And so we saw this in our last unit. As concentration decreases, rates of reactions also decrease. So the first reaction is going to produce some N2O4. So it says after N2O4 is produced in the first reaction, the second reaction begins to take place. Now this reaction is slow at first. Why? Well, you have just after the reaction begins, very little N2O4. So the concentration is really low. So that means the rates of that second reaction is going to be really low at first. But this reaction will speed up. It'll go faster as time goes by as the concentration of N2O4 increases. So as the first reaction produces more and more N2O4, the concentration of N2O4 increases, and that then will increase the rate of reaction number 2. So essentially, first reaction is going to slow down. Second reaction is going to speed up. At some points, the rates of these reactions will equal out. And when the rates of these two reactions are equal, we say a state of dynamic equilibrium exists. An equilibrium system is a dynamic system. What does that word dynamic mean? It means changing, ever changing. What is the opposite of dynamic? The opposite of dynamic is static. Balance. So when we think of the word equilibrium, think balance. We have this state of changing balance, ongoing change, yet balanced. We'll see what I mean in just a second. All right, let's start off with a graph of amount versus time. Now, I'm actually going to draw two graphs in that space at the bottom of the notes there. So let's set up our axes, and we're going to draw two graphs. Let's set those up. I'm going to put amounts. This could be concentration. Amounts on the y-axis and time on the x. And same thing over here. All right, and so let's go ahead and color coordinate this. So I'm going to use blue for the NO2, and we'll use green for the N2O4. So this will be on both graphs. So let's start with the NO2. The amount of NO2 at the very beginning, so time 0 here, is pretty large. And so we said that the amount or concentration is going to decrease during the course of the reaction. And as we saw last unit with kinetics, the amounts does not decrease linearly with time, but instead exponentially. And so we get something like this for the NO2. How about the N2O4? So initially there's none. So we're going to start right there. It's 0. 0 N2O4 in the container. But as reaction 1 occurs, then the amount and concentration of N2O4 is going to increase. Again, not linearly with time. But something like this. And we get maybe something like this situation. So what happens at about right here after this long during the reaction? What do you notice about the amounts of the NO2 and N2O4? Well, at some point, the amount of NO2 stops decreasing and the amount of N2O4 stops increasing. At this point, we say equilibrium has been reached. Now, what is true about the amounts of these substances at equilibrium? They become constant. Again, the amount of NO2 stops decreasing, the amount of N2O4 stops increasing, their amounts become constant. Now, it looks like it kind of goes down here, but that should just be straight across. So when the amounts become constant, we say the system has reached equilibrium. What would this look like? What would you see? What would the observed changes be in the system? So again, NO2 is a dark brown gas. Pause the video and think about what you would see over time. So what would happen to the brown? The brown would get lighter as the concentration of NO2 decreases. At some points, though, that brown would stop fading, and the appearance of the that gas, that mixture of gases, would look like nothing's happening. So macroscopically, systems at equilibrium appear static. It looks like from our observations, nothing's happening. It's not getting any darker. It's not getting any lighter. It reaches a point where it just maintains a light brown color because we still have, even at equilibrium, some, right? How much do we have? We have some NO2 in the container. Now that's one situation. And it's not always that way. So let's take a look at our second graph. So once again, we start off with the amount of NO2 being very high. Its amount decreases. Same thing with the N2O4 as before. Its amounts at the beginning is low, 0. And over the course of the reaction, its amount increases. So again, I'm going to label these over here so you make sure you know what they are. Once again, we see that the amount of NO2 stops decreasing right about there. and the amount of N2O4 stops increasing. At this point, we say the system has reached equilibrium, dynamic equilibrium. Now, what's the difference between the two graphs? What is different about the amounts of these substances at equilibrium? Well, graph number 1, we'll call it the one on the left, shows that at equilibrium, there is more N2O4 than there is NO2. Highly possible. The second graph, graph number 2, shows that equilibrium, there's more NO2 than N2O4. That is also possible. So it can be either way. Now, how do you know if there's going to be more NO2 or more N2O4 at equilibrium? We'll learn about that later. Next, let's make a graph of rate versus time, reaction rate versus time. So let's set up our axes. Just one graph this time. So we have rates on the y-axis. That could be molar per second or whatever. And then we have time there. And again, I'm going to color coordinate it. So blue is going to be reaction 1 from equation 1. And then I don't want to make this appear like they're the same graph. So I'm going to pick a different color. Let's go with, I don't know, we'll go with that pink. And this will be reaction 2. So again, I'm referencing these equations. So 1 and 2. In fact, if we want, I can make them match their colors. Whoops, I do not want purple for that one, or pink. That's 2, and that's 1. There we go. All right, so let's take a look at this graph. So we'll start off with reaction 1. What do we say about the rate of reaction 1 initially? We said the rate of that reaction was high. And then what happens to the rates of that reaction over time? It's going to decrease as the concentration of NO2 decreases. Now, how about this? And we talked about this in our last units. Does rate change with time or not? Is the rate of a reaction constant over the course of that reaction? I think there was a question like that on your test. True or false, the rate of a reaction is constant over time. That is false. It is not constant. It changes. And so again, we're going to see a decrease, not linearly, with time in the reaction rate. So something like this, perhaps. Reaction number 2. It is slow at first, but its rate will increase as the concentration of N2O4 increases. And again, it's going to increase not linearly with time. So we get something like this. So what do you notice right there? This many seconds or minutes or whatever after you put the NO2 gas in the container. We see that again, what's on the y-axis? Rates. The rates are equal. When the rates of the two opposing reactions are equal, we say the system has reached equilibrium. Now, something to be careful of in looking at the two graphs. Equilibrium does not mean equal amounts. We do not have equal amounts of NO2 and N2 at equilibrium. Here or here. So make sure you understand that equilibrium does not mean equal amounts. Could the amounts of NO2 and N2O4 be equal at equilibrium? Sure, they could. That's usually not the case. Here we see at equilibrium, we have equal rates. Equilibrium means equal rates. So, in summary, macroscopically, what we can see with our eyes, equilibrium has been reached when the amounts of the reactants and products are not changing. Their amounts become constant. Submicroscopically, going back to this graph here, look at the rates. At equilibrium, the reactions are still going. So submicroscopically, equilibrium has been reached when the rates of the two opposing reactions are equal. Now, be careful with these next two here. An equilibrium situation may only be achieved if no substances are entering or leaving the system. This is known as a closed system. Now, in our example here, it was a closed container. It doesn't have to be. It does have to be a closed container if you have any gases involved in the reaction, so you don't want them to just escape. But a closed system could be a solution. As long as nothing enters or leaves that solution, that technically is a closed system. Secondly, equilibrium situation may only be achieved if a constant temperature is maintained. If you change the temperature of that system, then it's going to have an effect on that system. So let's do this. Instead of writing two different equations for the opposite reactions, we can write one equation showing both reactions that are occurring. And so here's what we do. We're going to draw a two-way arrow or double arrow, equilibrium arrow. So we can read this equation from either left to right or right to left. So this double arrow means that the reactions are proceeding in both directions at equal rates. Later on, I'm going to show you a situation like this, where you have two opposing reactions that are not occurring at the same rate. Likewise, we could get something like this. So if the length of the arrow, when I draw it out, the length of the arrow represents the relative rate. And if the lengths of the arrows are the same, that means the rates are equal. If the lengths of the arrows are not the same, then that means the rates are not equal. All right, so let's define these reactions. There's names. When we read the equation for the reaction from left to right, this is known as the forward reaction. And when we read the equation from right to left, this is not the backwards reaction, but rather it is known as the reverse reaction. Let's look at some examples of equilibrium systems. One such example is vapor pressure equilibrium. So let's say you take a container. Let's draw a container here. Fill it up with some water and close the container. All right, so what's going to happen to the water inside this container? Well, water is a liquid and all liquids evaporate. So that means some of the water is going to turn into a gas. So the arrows pointing up represents evaporation. Now those molecules in the gaseous phase, they're moving around, and it's possible that they collide not with this wall here or here, this top, but maybe they collide with the surface of the water. And in doing so, they will rejoin the liquid state. What do we call that process where a gas turns into a liquid? That is known as condensation. So eventually, and I try to show this with my arrows here. If you notice, I have 5 arrows pointing up, 5 arrows pointing down. The rate of evaporation is equal to the rate of condensation. So again, as I talked about before, not a chemical change in this case. This is a physical change. Nevertheless, this is an equilibrium system. So let's go ahead and write the equilibrium equation, we call it. So again, going back to here, this is called an equilibrium equation, where we have a forward and reverse reaction. So here we have this. So we have liquid water on the left, we have water vapor on the right, and the equation read from left to right, is the equation for evaporation, and the equation read from right to left is the equation for condensation. Here's another example we'll talk about later on in the year is a saturated solution. A saturated solution is an equilibrium system. So let's go ahead and draw what that looks like. So again, you have a container, put some water in that container, and then make a saturated solution. So remember, what does that mean, saturated solution? A solution that contains the maximum amount of solute dissolved and in fact has undissolved solute sitting on the bottom of the container. So again, though, we are going to have particles in solution. These could be ions or these could be molecules, as I'll show you in a little bit. And technically, this solid is still dissolving. So the arrows pointing away from the solid represent the process of dissolving or dissolution. At the same time, though, we have some of these particles that are in solution rejoining the solid. What is that process called where you go from aqueous to solid? So solid to aqueous is dissolving. So those arrows pointing back to the solid are the opposite of dissolving, which is known as crystallization, crystallizing. Crystallization, process of changing from aqueous back to solid. So in a saturated solution, you have both the dissolving and crystallizing processes occurring at the same time and at equal rates. Now, there's a couple different ways we can write the equation here for this type of equilibrium system. For molecular solutes, let's say you have a saturated solution. I'm going to draw this up here a little bit because I'm running out of room. Let's say you have a saturated solution of sucrose. So sucrose has a chemical formula C12H22O11. Saturated solution, so we want a two-way arrow, double arrow, equilibrium arrow. And what happens to the sucrose in solution? Well, it doesn't dissociate. It's not made of ions. But the solid particles will break apart into individual molecules that, of course, are in the aqueous phase. They are surrounded by water molecules. So that's the case if it is molecular. How about ionic? Let's say we have a saturated solution of sodium chloride. Again, saturated, so we got two-way arrow. This is an equilibrium system. This time in solution, we are going to have aqueous ions. And so a little different situation for molecular versus ionic solutes. Another example of an equilibrium system is gas phase equilibrium, kind of like what I showed you at the very beginning. You have the nitrogen dioxide and dinitrogen tetroxide system. Here's another one. Let's say you take some nitrogen gas and mix it with hydrogen gas and then close that container. That reaction is going to produce ammonia gas. That ammonia gas can actually react with other ammonia molecules to reform nitrogen and hydrogen gases. So this is also an equilibrium system. What if you took some sulfur dioxide gas and mixed it with oxygen gas? They would react to produce sulfur trioxide gas, which, like on our previous example, can react to reform sulfur dioxide and oxygen gases. So gas phase equilibrium, where everything in that system is a gas. One more, which will have quite significance, large significance later on. Solutions of some acids and bases exists in or as equilibrium systems. So I'm going to throw out a word that we'll talk more about later. Solutions of weak acids and weak bases are equilibrium systems. So both weak acids and weak bases are weak electrolytes. They are so-so conductors of electricity. We'll talk about that next unit. So let's write an equation showing the ionization of a weak acid, that acid being hydrofluoric acid. So it does not ionize completely, and so we end up with an equilibrium system where we have H3O plus and F minus ions in solution along with are HF. So all of these substances are in solution at the same time. An example of a weak base is ammonia. So ammonia can react with water to produce ammonium ions and hydroxide ions. And again, once again, all of these substances are present in solution, of course, with the water. Right, I think that concludes this lesson. Next time we will talk about something known as the equilibrium constant, and we'll do some calculations involving equilibrium systems. Thanks for watching.